Hello everyone, thank you for joining today's webinar. I'm Sumit Singh, an electric motor expert at Aimworks. Aimworks is a leading provider of electromagnetic simulation software for electrical and electronic design from DC to millimeter wave frequencies. Our products are embedded in the most popular CAD platforms, namely SolidWorks and Inventor. They cover a wide range of applications ranging from electric motors, generators, transformers, and power electronics at the low frequency end of the spectrum to antennas and various wireless circuits and components at the high frequency end of the electromagnetic spectrum. I request all the participants to please feel free to ask your questions using the chat box option, and we will address all of the questions at the end of the presentation. Here is today's agenda. First, we will discuss about an BLDC motor and its working principle and its application. Then, we will go through some of its design challenges and what are the different Aimworks solutions we have. Then, we will look at the design specification of the brushless DC motor, and we will perform no load study and full load study under 120-degree mode and 180-degree mode voltage commutation. Later, we will demonstrate you with our Aimworks 2D software and concludes today's webinar. The term DC motor is traditionally used to refer to brushed DC motors. In the DC motor section, we have seen that brushes are required to convert alternating current generated in DC generator to direct current, and vice versa for DC motors. We have also seen that a field winding is used to produce the magnetic field required for energy conversion. If the winding is replaced by permanent magnets, the rotating magnetic field is then generated without the need of separate winding. Besides, the losses in the field will be eliminated. There has been a significant improvement in permanent magnet technology in the last few years. The permanent magnets are alloys like neodymium iron boron, which is nothing but NdFeB, and samarium cobalt that have become popular in recent years. Now, if permanent magnets are placed on the rotor surface, the armature winding will be stationary and hence brushes can be removed. This has two advantages. First, resistive losses in brushes are eliminated, and the second, maintenance and safety issues are also taken care of. Thus, the DC motor with permanent magnets without brushes is called nothing but a brushless DC motor, or simply BLDC motor. Here are the differences between the brushed DC motor and brushless motor. So if you look at its rotor structure, brushed DC motor has a coil winding and brushless DC motor has permanent magnet mounted or buried inside the rotor cores. For commutation, for brushed we have a commutator and brush as it's said in the name, and we need an inverter circuit to run BLDC motor. And we need also to detect the rotor position so that we can excite we can turn on or turn off the particular inverter switches. In terms of heat dissipation, the BLDC motor has a great dissipation of heat as the heat is generated in the external stator and it is connected to the enclosure casing of the motor, which has a fins to radiate the heat generated within the motor, and it's easier to cool. Whereas in brushed DC motor, we have a coil circuit in the rotor and it concentrates all the heats within the rotor. Next, talking about the durability, since brushless DC motor doesn't have any brushes and the rotors are mounted with magnet, so it has a more reliability compared to brushed DC motor, whereas these brushes get wear and tear over a period of usage. In terms of price, I think the brushless motor will be a little expensive because it needs a drive circuit to run or to drive the brushless motor. So in overall, if we compare, the brushed DC motor are ideal when the cost is low. We need a simple motor and efficiency are the priority. But brushless motor can be also used when you need a higher efficiency, but when you need to control your motor more accurately and more longevity is required, then we take brushless motor as a priority over brushed DC motor. So let us look at the working of principle of the brushless DC motor. So the BLDC motor works on the principle similar to that of a brushed DC motor. The Lorentz Force Law states that whenever a current carrying conductor is placed in a magnetic field, it experiences a force. As a consequence of the reaction force, the magnet will experience an equal and opposite force. In the BLDC motor, the current carrying conductor is stationary and permanent magnet is moving. So when the stator coils get a supply from the source, it becomes nothing but an electromagnet and starts producing the uniform field in the air gap. Though the source of DC supply switching makes to generate an AC voltage waveform with a trapezoidal shape. Due to the force of interaction between the electromagnet stator and permanent magnet rotor, the rotor continues to rotate. With the switching of windings, as you can see on the figure right hand side, where the particular stator coils are switched in a fashion as you can see in the inverter drive command, and the corresponding winding are energized as north and south poles. The permanent magnet rotor with north and south poles align with the stator poles, which causes the motor to rotate. So far we have discussed a permanent magnet based BLDC motor, but there is also very popular motor used in a lot of automotive industry are the permanent magnet synchronous motors. So how they are different to each other? In terms of construction, both the motor looks very similar to each other, but still they have significant differences. First, the main difference is that BLDC motors are fed by the direct current, whereas the PMSM motors are fed by the sinusoidal current. And the way the BLDC motors are wound, maybe concentrated winding, it creates a trapezoidal back EMF, and whereas the PMSM motors have sinusoidal back EMF, as you can see in the picture on right hand side. In case of BLDC motor, only two phases are excited at the same time, whereas in PMSM it is possible to excite all three phases at the same time. And since due to this excitation switching between the phases, the BLDC motors have a higher torque ripple during the commutation, whereas PMSM machines doesn't have a torque ripple when they commutate between the phases. So brushless DC motors are used in wide variety of applications, ranging from varying loads to constant loads, and even positioning application in the field of industries, automotive, aviations, and like automation systems, and even like medical equipments, and many more. In our today's webinar, we are considering 120-degree conduction mode and 180-degree conduction mode. Now let's just understand what this conduction modes actually represents and what does it mean. So for the 120-degree technique, in this case, the current flow through the two phase A and B from the positive end of the to the negative end of the DC bus. As you can see in this picture, I am just pointing my cursor, okay? And while the remaining phase C, which is like represented by the dotted lines, remains floated. In this switching scheme, each phase was switched on for 120-degree electricals and switched off for 60 electrical degrees. The next switching states for phase B was the power transistor Q5, as you can see here, was switched on for the next 60 electrical degrees. The phase voltage in this mode is VDC. Whatever is, we have a DC bus voltage, so we get a phase voltage peak as VDC by 2, and its output voltage waveform and phase and its line to line voltage are shown at the bottom of this 120 degree technique. Now, unlike the 120 degree technique, for the 180 degree technique, the three phases, that's A, B and C, are switched on at any time. This means that either the upper side or the lower side power transistor of the same arm are switched on at any time. The current in this case flows through from the positive end of to the negative end of the DC bus. The current of phase A was equal to the sum of both phase currents B and C, but of course and sign is inversed. The value of the phase voltage in this mode is either VDC by 3 or 2 VDC by 3. As you can see, it's in two steps. So the first one is VDC by 3, and then the peak, that is a second step, is 2 VDC by 3. Its output voltage waveform, phase voltage and line to line is shown here in the bottom part. In comparison to 120 degree conduction mode and 180 degree mode, we can see the voltage level is different, and hence this can also affect the motor performance. As we can see here, we have VDC by 2, and there we get a magnitude of voltage up to 2 VDC by 3. So obviously the current induced will be different, and then which will lead to a different torque. So to begin with any BLDC motor, there are few challenges, the few choices that designer has to make. First, what should be the rotor pole number, and to simulate this BLDC motor with different rotor pole number and different winding configurations to evaluate its performance. Also, once we have the model ready, we need to obtain its performance at no load and full load conditions and get the parameters such as electromagnetic torque, back Emf, Cogging torque, and the saturation areas in the rotor core or the magnet core, and the direction of flux. So there are many other different parameters that need to be analyzed. And since in our webinars we are talking about the different mode of excitation, so how does the motor behave in 120 degree excitation and 180 degree excitation? That is also one of the challenges, and to which we need to find it out. And then to evaluate the rise in the temperature, which is like heat generated in both the motors. So well, to analyze and to evaluate the motors, we have different solutions. First, we have the Motor Wizard tool. It is a template based motor design software that allows user to accurately solve both electric and magnetic problems. It includes electrostatic, magnetostatic, and transient solvers equipped with integrated analytical and finite element based solvers. Next, second, we have Aimworks 2D tool. It is a 2D electromagnetic simulation software that uses the FEA to solve magnetic, electric, and transient problems. Aimworks 2D allows you to study the effect of the geometry or simulation parameter changes on the design. It also allows to couple a transient magnetic study to mechanical motion and thermal. And the last, we have EMS tool. It enables user to do both electric and magnetic simulations, but using the complete 3D geometry. EMS is a true multi-physics software that enables user to couple the magnetic and electric design to circuit, motion, thermal, and structural analysis on the same model in a hassle-free integrated environment. So today we will be using Aimworks 2D to simulate our BLDC motor. So let's look at its design specification. So we have considered a 24 slot, 16 pole and 20 pole configurations with the base speed of 4600 radian per second, which comes as 766 RPM. We have set the DC bus voltage to 150 volt, and the stack length of our motor is 100 millimeter, and we have chosen the core material as M27 grade of steel, and our conductors are obviously the copper windings. So before to begin the performance in Aimworks 2D software, first is to set the different parameters such as the material of the motor. So in our database we have a wide range of materials to assign to our rotor cores, stator core, for the windings, and for also for the different varieties of permanent magnets we have. Then the next part is to set the boundary conditions, where we select an air region as outer air region where as a magnetic vector potential, and then the next part comes is the force or the torque calculation. So there we select all the faces or the parts of the rotor core which is like rotating, and will be torque, and the portion of the motor where the torque will be computed. Then once we have done with the model settings, last step is to set the mesh for that, and you can easily control the parameter that if you want finer mesh, or if you want run for a quick, like if you want to get a result quickly and you don't care about the accuracy, you can set a control the mesh parameter control, because obviously in a 3D geometry or any kind of FE analysis the mesh parameters matters a lot. And then next comes finally the excitation part, either it is current source or voltage source controlled, and you can set its frequency, its amplitude, or if you want even its a duration, how much cycle you want to run. So these are the basic which you need to set before you run your simulations. And once you run the simulation based on your geometry size and whether it's 2D or 3D, it will take its own time and the level of accuracy you have selected, and you will get your motor results. So to begin with, first here I would like to show you the no load flux linkage. So you can see for the 16 pole and for the 20 pole, since as the number of pole is increasing, we have a different frequency for each motor. So you can see the flux linkages are fine, very close to sinusoidal, and all the windings are perfectly balanced, and the magnets are good enough as it creates a flux linkage of around 0.12 Weber. Next is the back EMF. So here is an interesting point to note. In case of 16 pole, the slot per pole per phase ratio is around 0.5, and whereas for 20 pole the SVP ratio is 0.4. So obviously based on the short pitching and the combination of slot pole, you can get your back EMF as completely sinusoidal, even though if it is BLDC motor. And as you can see for the 16 pole, it has a not perfect sinusoidal, and it represents some kind of trapezoidal waveform. Next interesting parameter to observe is the magnetic flux density and its saturation in different part of the rotor. As you can see for the 16 pole design, the saturation is close to 1.5 Tesla because it has a less amount of magnet volume, and therefore since the stator is same for both the design, and you can see in case of 20 pole design, the saturation occurring at the tooth of the stator body is close to 1.63 Tesla. Next we have input voltage, which we are going to supply to analyze its on-load performance. In case of 120 degree commutation, we supply a voltage which is on for 120 degree and off for 60 degree. Whereas in 180 degree commutation, we supply for 60 degree at VDC by 3, for another 60 degree at VDC 2 VDC by 3, and so on. So we have this different commutation, as you can see here, which is supplied to the 16 pole BLDC motor windings, and we'll see its performance. So well, the induced current in case of 120 degree is comparatively less to 180 degree commutation mode, and that's obviously because the voltage applied in case of 120 degree was around 75 volt, which is nothing but VDC by 2 of the DC bus voltage, whereas for the 180 degree commutation we have a higher current induced, since it has a peak phase voltage of close to 100 volt, which is nothing but 2 VDC by 3. Therefore the induced current in both the mode of commutation is different, and then this lead to difference in the torque magnitude also. So as you can see, the average torque here is little lesser compared to the 180 degree mode commutation in case of 120 degree commutation, and you can see the torque ripple is a little higher, but if you go with a current excitation you might get a stable torque with commit ripple at each commutation. But since we have driven our motor or tested the performance of our motor using a voltage driven coils, therefore we get a torque ripple such that, and which can be reduced if we skew either the rotor or stator cores. For this analysis we haven't skewed any of the part of the motor, and therefore we get such type of electromagnetic torque result. Next comes for the 20 pole design. The same magnitude of voltage is applied but at different frequency, because for 20 pole obviously the frequency will be different compared to 16 pole design. And let's look at its results, and a similar pattern was observed. The current was higher in case of 180 degree mode of commutations, and rest, if I compare the shape or the waveform, it's almost similar, just the magnitude is changing, and it's all due to the different voltage applied to both the cases. And then we have a torque produced by these currents, and again for 180 degree mode commutation we get a higher torque, average torque magnitude, and the ripples are almost similar to each other, or maybe we'll see in the summary table whether how it differs in case of average torque and torque ripple magnitude. Next we have a thermal study done in both the cases for 16 pole design and 20 pole design, and more or less the temperatures are almost same for both the motor, and we know the heat of source is the windings, and we did analysis for a steady state and where all the windings were excited together and to compute the temperature, and we can see that the temperatures are well within the limit of the insulations, and 144 degrees Celsius in case of 20 pole and 141 degrees Celsius in case of 16 pole. So if we compare all the cases which we have simulated today, let's look at one by one. The first thing is the phase back EMF. Now, since when we switch from 16 pole to 20 pole, we get better flux linkage and we get more amount of magnet volume. Therefore, the phase back EMF at the same speed of 766 RPM was higher in case of 20 pole design and lower for 16 pole. And we can see there's a difference of nearly 19%, I would say. Then the next is the DC bus voltage, which is same for all the mode of commutation in both the design, whether it's 16 or 20 pole. We kept the DC bus voltage same so that we can have a comparison analysis between this design. But obviously when we go for a 120 degree mode, the peak voltage we get is 75 volt, and for 180 degree we get for 100 volt, and which is very similar to in both the cases. The induced current was higher, obviously, from 17.8 amperes to 89.5 amperes, and similar pattern was observed in 20 pole design. But now it's interesting to note here that we see a different magnitude of the current induced in case of 20 pole and 16 pole. The main reason is for 20 pole design the winding configuration is not the same as 16 pole, and therefore due to difference in its phase resistance, the induced current magnitudes are also different in both the design. Then last comes the torque magnitude, average magnitude, and its ripple, which is also higher for 180-degree mode of commutation. And it was also interesting to see here that the ripple somehow reduces, and it's result because we supply voltage in 2 steps. Therefore it's fundamentally more closer to sinusoidal, and therefore since the voltage has lesser harmonics compared to 120-degree mode, therefore somehow it also contributes to reduction in the torque ripples. And finally we have also obtained the power, and since the magnitude of induced currents are higher in case of 180-degree mode commutation, therefore we get better torque, and since the speed is same and difference in the torque, we get difference in the power, and 120-degree mode conduction leads to a higher power output from the motor. So in today's webinar we simulated a BLDC motor with 2 different configuration of slot pole combination. One was 24 slots with 16 poles, and the second was 24 slots with 20 poles. And we evaluated its electromagnetic performance, thermal, and finally we also had a comparison analysis using our Aimworks 2D software. And as I said in the summary table, it was observed that the back EMF of the 20 pole design is increased by 19% compared to 16 pole design, and it's all due to the increase in the amount of magnet volume. In comparison to the 120-degree mode commutation, we also observed that for the same DC bus voltage, the phase voltage, the peak phase voltage was higher for 180-degree mode, and hence it leads to increase in the electromagnetic torque. Therefore, BLDC motor are being used, and it is taken as considered as an alternative solution to fulfilling the growing demand of electrifications. And but however, in a nutshell, we can say that the selection of motor topology, whether it's BLDC motor, PMSM, switch reactance motor, or maybe it's induction motor, it's always a trade-off between the constraints, size, volume, performance required, and also the cost involved to manufacture these types of motor. So let's move on into the software demonstration. So well, here we are inside a SolidWorks platform, and we have launched our Aimworks 2D motor software. I have some analysis performed for today's webinar, and I would like to show you how it has been done in the Aimworks 2D software. So let's start with the no-load analysis, and I have a CAD model of 16-pole design. So first I have set the materials, which I discussed in one of the slides, that we need to select the rotor parts, and I have taken to begin, first we have a magnet which is N28, then we have rotor core which is M27, and then we have a stator parts and different copper and M27 core, and then we have a band and outer air as air. Once we are done with the material settings, next comes the load resistance, where we decide the magnetic potential as outside air region. Then we use our rotor part as a force or torque calculation. So if you just double click, you can select the faces that you want to compute the torque, and then we choose a setting over here. Then we have a mesh, so I would like to show you the mesh. So well, here we have got the mesh of our simulation. So then the last part comes the windings. We have A phase, B phase, and similarly C phase. So here I can show you the windings for A plus and A minus, and you can also look at its direction of current excitations, what we have for our 2D analysis. Now I'll hide these symbols, and since we're in CAD platform, you can just get a front view again. So this is how we set the windings for all the 3 phases, and then we go to the result, and we see. But before this, obviously you need to run it. So you right click on the study and you click on the run button, and once you run, you can start looking at its result. We have a wide range of results, like its energy, solid loss, resistance, winding losses, flux, linkage, induced voltage, and many more. So since this was no load analysis, I'll be interested to see its induced voltage, which is nothing but the phase back EMF. And we have all the three phases, which you need to select, add into your parameters, and then plot preview, and there you get the phase back EMF. So similarly, you can see the different part of, like, even if you're interested to see the cognitive torque, so you can go to torque and click, and then you can plot its cognitive torque. Even if you are interested to look at its magnetic flux density, you can just right click, you can choose different types of plot, either French plot, vector plot, contour lines plot, or fill lines. You can also use overlay as mesh or contour lines with combination of these plots. So let's see the French plot, and here you get the different part of the saturation, different part of the motor, where you can see how it is saturated. So well, there are different types of results like magnetic field intensity, applied current density, and many more. Similarly, here the interesting thing was, like, for the no load analysis, we used in current driven coils, and the current excitation was 0. But now once we switch to voltage commutation mode, here if we just copy the study and we change its properties for the winding, we, instead of current driven coil, we have used a voltage driven coil, and then we go to voltage source, and for each phases, like for phase A, you can, or for all the type of phases, either you can supply a DC voltage excitation, or you can give even sinusoidal voltage or different exponential or pulse voltage. The important thing is here is that to generate such type of pattern, it would be hard to generate with this just using a pulse voltage sources. So you can even import your voltage time curve using your Excel sheet, and then we have for phase A, for phase B, and similarly for phase C for 3 different cycles. And you can set the study time duration, and that is how you get different results for the 120 voltage mode of commutation. And similarly for 180 degree voltage commutation, I have excited the coils using a voltage driven, and then we have a 2-step from VDC by 3 and to VDC by 3 for phase A. Similarly, phase shifted by 120 degree for phase B, and then for 20 degree again compared to B phase, which is nothing but phase C. So well, here are the settings and the few results, the way you simulate using an Aimworks 2D software. So next is, here are the references which we have referred to simulate and to get the introduction part of this webinar. So I thank everyone for attending today's webinar, and now this session is open for a Q&A part. Thank you so much.